Can you all see my screen now?
Yes, ma'am.
Okay. So I hope you all can see the PowerPoint presentation. Okay, so this is the topic that we are going to cover now, electrostatics, and this is your subject code, PHSGCC2 theory. Um, Now, all of you have done electrostatics in your high school, and as far as I know that CBSE and ICSE, they have quite a few topics covered pretty elaborately in electrostatics. Those who have prepared for the joint entrance exams, you must have done several sums on electrostatics too. So I presume that you have a fair idea of the subject, and we will only be sort of developing on those ideas further according to the syllabus that has been prescribed by the university for your course. All right. So let us first go over a little bit on discovery and early observation. So basically, what we will be doing in today's class, I think that will mostly be a recapitulation for you, apart from the fact that maybe you have not done the forces etc. in the vectorial notations in your class 2, but now all that we will be doing will be in vector notations. Okay. Now let us go back to how electrostatics was discovered. Now this is a pretty old phenomena that has been observed by humans. Okay, so this is the natural phenomena that is static electricity. It was known from ancient times, okay, and discovered, as you can see, as early as 600 BC. So it is a very old phenomena, one of the earliest scientific phenomena, earliest natural phenomena that humans observed and started to study. All right. So this is the picture of a piece of amber. Okay, amber is a naturally occurring material which is sort of a stone-like thing and is mostly used in jewelry making, decorative items. So it was seen that when amber was rubbed with wool or silk or some other, I have shown a picture is rubbed with a piece of cloth, a silk cloth. Okay, even if it is done with wool or cotton cloth etc., it is seen that if you now take the piece of amber to light materials like feather or pieces of paper, then it is seen that the piece of amber attracts these light materials. Someone's microphone is unmute. Can you please mute your microphone? I can hear some noise. Please mute your microphone. Okay, so as you can see that amber here, this person is just holding the piece of amber and it is attracting these light materials. Here I've shown a picture of feathers. You can take pieces of paper also. So there must be some property developed in amber due to this rubbing with a wool or silk cloth that it can attract other materials which it normally cannot. Okay, please unmute. Okay, so now ordinary matter, we know that in ordinary matter the charged particles that are electrons or protons, they are present in equal amounts, right? In an atom there is an equal amount of electron and proton given by the atomic number of that particular element, and therefore any ordinary matter is electrically neutral because the number of positively charged protons and the number of negatively charged electrons in the atom are equal, hence rendering the object electrically neutral. Now, if a body is charged as we can see here in the amber case that since it is attracting the feathers, it must be there is no magnetism here, so there must be something else which is we are calling charges. So when it is charged, then there must be some excess of electrons, deficit of electrons. Now I'm not saying excess or deficit of positive or negative charges because it cannot be protons. You know that protons cannot be taken out of atoms. Protons are present in the nucleus. Electrons travel in orbits, and the outermost electrons, the electrons that are farthest away from the nucleus, are loosely bound to the atoms, and therefore some certain forces can be large enough to tear these electrons away from the atom. So when electrons are lost from an atom, then the number of positive charges become higher than the number of negative charges. So this atom becomes positively charged. And the atom that gains these electrons, there the number of negative charges become higher than the number of positive charges, and then that particular atom is negatively charged. All this you know. Okay. So a charged body means excess or deficit of electrons. Either there are more electrons than the normal number, or there are lesser electrons than the normal number. More electrons means it is negatively charged, lesser electrons means it is positively charged. But we must remember that in this process, there is no creation or destruction of charges. Okay, we must always keep in mind that electric charges, the number of electrons in the universe is a constant. We cannot create or destroy charges. So when amber is attracting feather, charges have not been created on the surface of amber. When amber was being rubbed with silk, there had been, due to friction between silk and amber, some loosely bound electrons got transferred from one object to the other. And therefore, the object that lost electrons became positively charged and hence gain the ability to attract lighter materials. And the object that lost electrons, that gained electrons, became negatively charged. Okay. Now I'm sure all of you have observed this phenomena. You must have combed your hair with a plastic comb several times and then held the plastic comb on bits of paper to see that the bits of papers are attracted towards the comb. This happens more in winter because there's a dearth of moisture in the air and on our skin. So this is where it's moisture, the transfer of electrons to bodies not so easy. So, but when the air is dry, when our skin is dry, when we are not sweating, for example, in winter, if you sit on a plastic chair, if you have not observed it yet, I would like you to observe it next winter. If you sit on a plastic chair and you put your hands on the handle of the chair, then you'll see that after some time, the hair on your skin, okay, that sort of, gets attracted towards the chair handle. I'm sure all of you have observed. I'm sure some of you have got an electrostatic shock from holding a metal rod or a metal handle in winter months. I mean, this happens to me several times. Whenever in winter I try to get down from a bus and hold the metal rod, I get a shock. So it just happens because there is friction and there is transfer of electrons between two bodies which rub against each other, and therefore there is this, when you hold the metal rod, the metals have a lot of electrons and they quickly pass to your body and you get that temporary shock. Okay, but we must remember that in this phenomena where frictional electrification is occurring. There is no creation or destruction of objects. During rubbing, electrons are just transferred from one body to another following the electrostatic series. Now, what is the electrostatic series? I have not given the electrostatic series here because it is not very important, but just if for your information, if you want to know, that this is a series where the materials are listed in order. Yes, do you want to say something? যে আনমিউট করেছো, কিছু বলবে? Okay, so during this rubbing, electrons are transferred from one body to another following the electrostatic series, and in this series, materials are listed in order. For example, paper, skin, wool, amber, hair, etc., etc. I don't remember this order by heart, but just that the order, that list will tell you which object will be positively charged and which object will be negatively charged when rubbed against each other. Okay, so which material loses electron and which material gains electron when rubbed against each other. All right. Okay. Just remember that the sum of positive and negative charges as a whole on the two bodies remains zero. If you sum the total of positive and negative charges between the two bodies, then the sum total will give you the total charge to be zero. So charges have been transferred, but as a whole, the two bodies as a pair will remain neutral. Okay, so just remember that there is no creation or destruction of charges. In other words, this denotes the fact that electric charges are conserved. So conservation of charges is a very, very important thing that we must keep in mind. So just this is something important to know as a concept. You won't find this relevant when you will be doing problems, but it's a very, very important concept, and you must keep this clear in your mind that when you are seeing that electrostatically things are being charged by friction, as we often see in winter, we must remember that there is no charge has been created or destroyed. It has only been transferred from one object to another. Okay, and this is called conservation of charges. Now let us go through some facts that we already know, and as I told you that we will be building upon this in the syllabus that we will be covering. All of you know that there are two classes of electric charges. Okay, positive and negative, and those in the same class repel, and those in opposite classes attract each other. All of you know this. Like charges repel each other and unlike charges attract each other. So opposites attract, likes repel, and basically this law was given by a scientist known as Dufay. Dufay is this, we don't often state this as Dufay's law, but it is good to know who first proposed this. Okay, so this scientist known as Dufay first proposed this, observed and put it as a law that like charges repel and opposite charges attract. Okay, the electrical force acts along the line joining the centers of two charges. This also all of you know. If you have two charges, then you draw a line joining the centers of two charges, and the force will act along this line. And we also know that this force is proportional to the amount of charge on each of the objects. There were a number of observations. So we are talking about all this that we are writing down. All this is prior to Coulomb's law. Okay, so these were being observed and they were finally put together as a law by Coulomb. So we will be doing Coulomb's law next. But observations prior to Coulomb, scientists were already observing these phenomena, that the force acts along the line joining the centers of the two charges, that the force is proportional to the amount of charge on each of the objects, and there were several observations that show directly or indirectly that there was a inverse square distance dependence of the force. The force was proportional to 1 by distance squared. All right, so these were, as I told you, observations or inferences that were done in early to mid 18th century, so before Coulomb, and just a list of scientists who were going through, they were performing experiments. And if any of you are interested, then you can just Google these names. In fact, I have given these names for those students who are interested in the history of science. If you Google these names, you will find the pictures of the experiments related to the work that they were doing, and you will see that in those days, in such adverse circumstances where there were no proper laboratories, there were no proper instruments, how they had performed these experiments, they themselves acting as one of the objects of the experiment, how they had performed these experiments to get these results. It's really outstanding to think that we are so privileged to just read through and perform experiments. Well, we are not being able to perform experiments now. We are just virtually doing our classes. But when we are in the laboratory, we can just take the instruments and perform the experiments. It's so easy for us. Anyway, so now we will see what the fundamental problem is in electromagnetism. Okay, we will see later on, and in this module you will be seeing finally that electricity and magnetism are not two separate phenomena. Electricity happens due to electrons. When they are at rest or when they are moving, we get current electricity. And magnetism is also due to moving charges. Whenever a charge is moving, there is a magnetic field associated with it. All of you know this, Lorentz force. Okay, so it is not a good idea to separate electricity and magnetism. However, at the present module, we will be studying only not the magnetic phenomena, but only the electrostatic phenomena. So what is the fundamental problem? The question is, what force do some electric charges, Q1, Q2, Q3, etc., that are called source charges, see, source charges, exert on another charge Q, which is called the test charge. So you have several charges Q1, Q2, Q3, etc., which we call source charges. And if you bring another charge Q, a lone charge Q, which we call the test charge, and then what force will this test charge experience due to the presence of these source charges? This is the fundamental problem. Okay, given the position of the source charges, the trajectory of the test charge is to be determined. Okay, so whenever there is a force acting on a body, then that determines the trajectory of the body, right? All of you, I hope, understand the term trajectory, the path of motion of a particular body. So when you are bringing the test charge Q to a region which already has several source charges, then the force of these source charges on Q will determine what path it will take. Okay, so this is the problem that is to be addressed. And when the source charges are stationary, that is when Q1, Q2, Q3, etc., the source charges, when they are not moving, then the topic is named electrostatics. Static means something which is not moving. Okay, so this is the general problem, that what is the force exerted by the source charges on the test charge. And we now go into the specific problem when the source charges are static, and that particular case is the case of electrostatics. All right. Now, what is the fundamental law of electrostatics? Coulomb's law, all of you know Coulomb's law. What does Coulomb's law say? The force acting on a test charge Q due to a single source charge small q is given by this. Okay, force is equal to some constant q by r square, r vector, where you have this charge, this is the source charge small q, and this is the test charge capital Q, and this is the distance between them, r. All right, so small r is the separation vector when you give the vector sign, and this k or kappa is the proportionality constant. Clear to all of you? Now let us look at it in a different way. Suppose we have a particular point charge q1 and another point charge q2. We don't call them source and test now. We have two charges, so we just call them q1 and q2. Okay, and the distance between the two charges, we call the distance between the two charges r21. Okay, the straight line joining the two charges q1 and q2 has a magnitude r21. Okay, so this is the more elaborate statement of Coulomb's law. 2 point charges q1 and q2 separated by a distance r21 exert on each other a force that is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. I hope all of you know this law, Coulomb's law. So now we write the force between them as F21 with a vector sign, proportionality constant kappa, directly proportional to the product of the charges q1, q2, and inversely proportional to the square of the distance between them, r21 square in the denominator. And the direction is along the line joining the two charges, that is along the vector r21. So which is why I have written the unit vector. Now I will show you the vectorial representation of this law. How do we get the vectorial representation? Suppose this is my charge q1, all right, and its position vector with respect to some origin O is r1 vector. q1 is placed in space somewhere. So how do you know its position vector? You have to get an origin of your reference frame, and the position vector is the distance between q1 and your origin, and that is given by r1. Okay. q2 is another charge which is at a distance r2 from the origin O. So r2 vector is the position vector of the charge q2 with respect to our origin O. Therefore, the distance, the magnitude of the distance between q1 and q2 is denoted by r21. Okay, and what is the vectorial representation? What is the direction of this distance between q1 and q2? It is given by r2 minus r1, that is r21. So this is the direction of the vector joining the two charges q1 and q2, that is given by r21 cap. So this is the direction of the unit vector, which is why I have given r21. So I hope you can understand the logic of why we did the warm-up on vector analysis before starting electrostatics. So the knowledge of vectors and position vectors and unit vectors is important in order to understand this. So we saw earlier that the force acting between q1 and q2, that is F21 vector, is given by this expression. We saw this from Coulomb's law, right? Kappa q1 q2 by r21 square r21. So in the above expression, F21 is the force exerted on the charge q2 due to the charge q1. Okay, and R21 is the unit vector in the direction from Q1 to Q2. Now please be very clear in these things. When you are writing F21 to be the force, then it is the force exerted on the charge Q2 due to the charge Q1. Okay, and R21 is the unit vector in the direction from Q1 to Q2. When Q1 and Q2 are of the same sign, either both are plus or both are minus, then what will happen? F21 will be in the direction same as R21. So Q1, Q2, if they are both plus or both minus, so the sign of F21 will be the same as that of R21. So the force will be in the direction of R21. So you can see from this picture, if Q1 and Q2 are of the same sign, then the force acts in this direction. So what does that mean? Attraction or repulsion? Yes? You should answer this.
Repulsion.
Repulsion. We know that like charges repel, but you can see directly from this vector representation why they repel. Okay? Because the force is acting in this direction. This is the direction of R21. The force is acting in this direction. So obviously the charges repel. They try to move away from each other. So this means there is repulsion. On the other hand, when Q1 and Q2 are of opposite sign, Q1 positive, Q2 negative, or Q2 positive, Q1 negative. So F21 and R21 then will be in opposite directions. So when Q1 and Q2 are of opposite sign, then F21 is in a direction opposite to R21. So R21 is this side. So F21 will be directed in this direction. Okay, which means there is attraction. So all this while you sort of learnt up that like charges repel, unlike charges attract. Now that you know the vector representation, you directly can see why like charges repel and why unlike charges attract. It's straight away comes from the direction of the force related to the direction of the distance joining the two charges. All right. To get the force exerted on Q1 due to Q2, we said that this notation F21 is the force exerted on Q2 due to Q1. How do we get the force exerted on Q1 due to Q2? We just change the subscripts. So F12 is same constant, just Q2 Q1 by R12 square R12. So you just swap the position of the subscripts here. Obviously F12 is equal to minus F21. Okay, so the force on Q2 due to Q1 is directed just opposite to the force on Q1 due to Q2. Excuse me. So when you are calculating the force between two charges, then you have to keep in mind that you have to state which charge is acting on which charge. You have to state the force due to this on that or due to that on this, because the two have the same magnitude but different directions. So I don't know whether you paid attention to this thing earlier, to this matter in your when you studied electrostatics earlier, but just I want you to keep attention to this thing over here, that the two forces, the force on Q1 due to Q2 or the force on Q2 due to Q1, have the same magnitude but they are oppositely directed. So they are two different vectors. You have to remember that. Okay. Next, certain points to note. First, the vector, the unit vector in the direction of R21 is given by this, right? R2 minus R1 by mod R2 minus R1. So remember that if you are trying to calculate the force and you know only R1 and R2 and you don't know the value of R21, so this is the formula that you will be using. Okay. So this is just we are substituting R21 unit vector by this representation here. Second point, just remember, just keep in mind that we are referring to point charges here. What do point charges mean? Means that the charges are extremely localized and therefore considered dimensionless compared to the distance between them. So I'll just go back to the previous slide once more. So these are point charges, meaning that we don't need to bother about their length or breadth or radius, etc. Why? Because now you might say that a point like that does not exist. How will we, isolate a point charge like that? Of course, you are right. We cannot isolate a point charge like that. When we are treating it in this manner, it just means that the distance between them is much more compared to the dimension of a particular charged object. Okay, so if you have a small plastic ball that you have charged and say its radius is about 1 millimeter, then the distance between this charge and the other charge between which you are calculating the force may be about say 100 centimeters. So you can neglect this compared to the distance. Okay. So these are the 2 points that you have to keep in mind when you are looking at the expression of Coulomb's, the force between two charges as given by Coulomb's law. Now let us calculate it is very important to know the value of the constant kappa or k, that is the proportionality constant. And you must remember that this value is system dependent. It depends on the system or the medium in which you are considering the charges. So if you are in vacuum, k will have some value. If you are in air, it will have some other value. If you are in water, it will have some other value. So the value of the constant kappa is dependent on the medium in which you are working. Now we'll first calculate the value in CGS system. So if there are two like charges of equal magnitude and they repel each other with a force of 1 dyne when they are 1 centimeter apart, each charge is of 1 electrostatic unit. The unit of charge in CGS system is ESU, and then you can see kappa is equal to 1. Okay, so you can directly put it in this formula and see Q1 is 1 USU, Q2 is 1 USU, distance between them is 1 centimeter. So 1 by 1, and the force is also 1 dyne. So kappa is equal to 1. 1 equal to kappa into 1 by 1, so kappa is 1. So in the CGS system, the value of kappa is 1. In the MK system, that is the SI units, what will be the value of kappa? Here, how do we define the value of kappa? Two like charges, each of value 1 coulomb, when separated by a distance of 1 meter in free space, they repel each other with a force of 8.8975 into 10 to the power 9 Newton. Okay. So when two unit charges, that is two charges of 1 coulomb, same sign, which is why they are repelling each other. So when two charges, when Q1 equal to Q2 equal to 1 coulomb and they are separated by a distance of 1 meter, so 1 by 1, then it is seen that they repel each other with a force of this value, 8.8975 into 10 to the power 9 Newton. So in MK system, the value of kappa is 8.9875. Okay, this will be 9875 also. Just a second. Okay. So the value of kappa in the SI system is 8.9875 into 10 to the power 9 Newton meter square per Coulomb square. You have to remember the unit also. So in this case, it is we usually take kappa equal to 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space, and the value of epsilon naught is 8.85 into 10 to the power minus 12 farad per meter. So when you will be doing sums related to Coulomb's law, you need to keep in mind these three quantities. Okay, so the value of kappa in the SI unit, if it is in CGS system, well and good, you just take kappa equal to 1. If it is in MKS unit, then you have to remember that the value of, usually it is given in the problem, but it is better to remember these certain values. So kappa is 8.89 10 to the power 9 Newton. More important is the unit. Okay, if you put the values in the, if you put the units of the other things, that is force, distance and charge, then you will see that the unit of kappa is Newton meter square per Coulomb square. Kappa is actually equal to 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space and the value of epsilon naught is this. So epsilon naught and kappa are reciprocal to each other. So since the unit of kappa is Newton meter squared per Coulomb square, obviously the unit of epsilon naught will be Coulomb square per Newton per meter square. Okay, and that is actually the value of farad per meter. So these three boxed quantities you must keep in mind. All right. Okay. So now that we know Coulomb's law, and now that we know the value of the constant of proportionality in Coulomb's law, that is kappa, so basically we know what is the force exerted by one charge on another and vice versa. But as I told you in the beginning, that the problem is to find out the force exerted by several source charges on a given test charge. Okay. So for that, we will have to know the principle of superposition. Now I am sure you have come across the principle of superposition in several other things. You know what the principle of superposition is. From the name itself, you can understand that superposition means when you have more than one event happening together simultaneously. Okay, so I'll first tell you what the general statement of the principle of superposition is in terms of force. So basically, this is the general statement of the principle of superposition. The net force acting on a particle is the vector sum of the individual forces acting on it. The net force acting on a particle is the vector sum of the individual forces acting on it. You have a particular particle. So you have done this when you had studied forces and work per energy in your class 12 syllabus. You have a body on which not a single force but several forces are acting together. So what do you do in such cases? What do you do when there are more than one force acting on a particular body? Can someone unmute and tell me? Yes? Suppose you have a body on which two forces, say F1 and F2, F1 vector and F2 vector are acting together. How do you find out the resultant? What is the resultant force on the body?
By adding two forces.
By adding vectorially, right? Vector addition, correct? So the resultant force will be the vector sum of the two forces acting on the bodies, and that is, we call it the resultant. So what do we have to do in this case? In our case, we are not talking about mechanical forces, but we are talking about forces between charges. We are talking about forces that are given by Coulomb's law. So what do we do in this case? We need to find the interaction between all the source charges with the test charge. So in this case, what will be the statement of the principle of superposition? The interaction between any two charges is completely unaffected by the presence of other charges. Okay. So when there are several charges acting on a single charge, Q1, Q2, Q3, etc., acting on capital Q, we have to remember that the force of Q1 on Q is totally unaffected by the force of Q2 on Q or Q3 on Q. All these forces between the individual pairs Q1 and Q, Q2 and Q, Q3 and Q, etc., they are unaffected by each other. Okay? They will be just like that, only together they will be acting simultaneously, and you have to find the resultant. Okay, matter clearer? So to find the force on a test charge Q due to several source charges Q1, Q2, Q3, etc., we separately compute the individual forces of each source charge on Q and finally apply the principle of superposition to get the resultant force on Q. Okay. So suppose F1 is the force on Q due to the charge Q1. F2 is the force due to charge Q2. F3 is the force on Q due to charge Q3, etc. Then the resultant force on Q due to these three charges, or suppose there are other charges also, will be the resultant force F equal to vector sum of all these forces. F1 plus F2 plus F3 plus etc. up to how many charges are there, Fn. Okay. So suppose this is a charge Q3. We have a charge Q3. Now we have another charge Q1, and this is the distance joining Q1 and Q3. So what is the force on Q3 due to Q1? We know the force is along the distance joining the two charges, and it is given by F31. The force on 3 due to 1 is given by F31. We just went through this from Coulomb's law. We just learned this. Again, we have suppose another charge Q2, and this is the line joining Q2 and Q3. So what is the force on Q3 due to Q2? Given by F32. Force on Q3 due to Q2 is given by F32. So you can forget about Q1. You can forget about the presence of Q1 when you are computing the force between Q2 and Q3. And you can forget about the presence of Q2 when you are computing the force due to Q1 on Q3. Now suppose both Q1 and Q2 are present simultaneously and exerting their forces on Q3. That is, the forces F31 and F32 are simultaneously being exerted on the charge Q3. So obviously you can understand here that Q3 is our test charge and Q1 and Q2 are our source charges. So what is the resultant force on Q3 due to Q1 and Q2 simultaneously? Here we apply the principle of superposition, and this force is given by F, the vector sum of F31 and F32. Okay. So the resultant force F on the charge Q3 due to joint action of the charges Q1 and Q2 is obtained by addition of the individual forces F31 and F32. All right, so the resultant force F on Q3 is vector sum of F31 and F32. Now let us do the same thing in the notation that we have obtained from Coulomb's law, because that is what you will have to do in your sums. So Q1 acting on Q3 gives the force F31. Using Coulomb's law, what is the value of F31? This kappa Q1 Q3 by R31 square vector R31. Then we have Q2 acting on Q3 with the force F32. So F32 value is kappa Q2 Q3 by R32 square R32 vector, unit vector. So what is the resultant force on Q3? The resultant force F due to simultaneous action of Q1 and Q2. We just put the values of F31 and F32. Okay, so this is the resultant force. So if there are n test charges affecting, say, the jth test charge, this will be source charges, sorry, I'll just make that change. So the resultant force is these two. So if there are n source charges like this, Q1, Q2, etc., etc., and they are affecting the jth test charge. So in place of Q3, I write Qj, and there are Q1, Q2, Q3, etc., like that, n charges. Then the net force on the jth test charge is given by this. Fj is, see, Q3 is common in both terms. So you can take Q3 out, which means if there are n such terms, you can take Qj, the test charge, out. Kappa is there, so you can take kappa out common. So kappa is, we know, 1 by 4 pi epsilon naught. So Qj by 4 pi epsilon naught summation I equal to 1 to n, but remember I not equal to j, because Qj cannot exert a force on Qj. It has to be on any charge other than Qj. No charge, only charges which do not have the subscript j will exert a force on Qj, which is why I have given this I not equal to j. Okay, Qi by Rji square Rji vector. So this is the general expression when there are n test charges acting, n source charges acting on the jth test charge. All right. So suppose there are 5 charges and you are given their position vectors. So you can just sum up, use this formula and find the resultant force on the test charge due to all the source charges. All the information that you need is the magnitude of the individual charges and the distance between the test charge and each of the individual source charges. That magnitude you need to know, otherwise you won't be able to compute this. So you have to know the values of all the RJIs and the directions so that you can make this vector sum. So this is the final and general statement of Coulomb's law when there are not just two charges exerting force on each other, but n test source charges exerting a force simultaneously on a single test charge. Okay, so just for 2 single point charges you can apply Coulomb's law, but if there are more than 2 charges, then you have to apply the principle of superposition. Clear? So we'll end our class today.